Mike down there. Hey,
Like
good to see you again.
Yeah.
Just like old times. I like
We
it.
should be roommates now.
This is good. I can't wait till I can see you in person and we can work a lot more together. This is really good. I like this. So very good seeing you again. And let's see. Next up at 2 o'clock is Scott Barella from PESA. He's a CTO. And Scott, what are you going to talk about today, briefly?
Well, Kevin, today I'm going to talk about what we've been working on over the past year or so, and what we are bringing to the market space. I think you'll appreciate the tour. Let me go ahead and show my screen here. You should now have it.
Looks like PESA Virtual NAB and your name and title.
Very good. That'll do it.
Okay. I'm going to leave you at this point.
Everything's good? Okay, so what we'll do is we'll just go over. I am Scott Barella, the CTO for PESA Switching Systems. We've been working on a couple of things over the past several months, and we thought we were going to show you these all at NAB, but of course, because of the worldwide pandemic, we're going to do this virtually. So I thought we could kick off and show you just exactly what we've been had in store here. I'll give you a quick overview of PESA in general, what we've been working on with respect to our old products and some of our newer products, which is audio video over IP and the use of USB in that for KVM, and our security products and focus over these developments. I also want to show you what we've been working on with respect to the next generation media management system, which we're excited to kind of showcase. First off, PESA is about a 50-year-old company, and we've been around for quite a while. We recently moved, I say recently, I say in the last 10 years, we've moved over to more of the government and military focus in what they call a video distribution system, or VDS for short, and that's what we've been working on these many years, and as such, we are in a lot of command and control, commonly known as C2 environments, and video teleconferencing as well. But you know us in some other events as far as sporting, and we even oversee some of the rocket launches for some of our agencies that oversee the space program. VDS for America's warfighters is kind of where we're at right now, and we oversee a number of critical missions, and we're known to be very reliable, very robust, and above all, very secure. The Fusion platform is kind of where we've been starting, or where we've had in the past, and what we have in terms of a 12G or 12 gigabits per second HD SD, or 12G SDI payloads across an SDI coaxial connection in single link. We also do this in some smaller formats with 3G and some others, but everything below really 12G and lower we do on this platform. This is the largest platform for 12G routing. It has 320 by 320 cross points that you can connect to. We also have some very flexible arrangements on the external side of the router, which accounts for IP gateway cards or IP gateway sockets, so that we could have SFPs that will address the pieces and parts of our systems that offer not only low power consumption, but the ability to hot swap the cards on the fly. The Cheetah routers have been the stalwarts. These are the age-old guys that have been in the government services division for these past several years, and this past decade in particular. And it essentially goes from 64 squared platforms all the way up to 864 by 864. These offer extreme flexible solutions in terms of being able to embed and de-embed signals with a complete DRS router that goes along with it. These routers are renowned worldwide and have been used in a number of things, but they are all controlled by what we call the PERC 3000 system controller. The PESA Ethernet Routing Control 3000 system, PERC for short, has the ability to not only control our Cheetah and Fusion systems, but also some of our smaller systems for extreme redundancy and so forth. They interface directly with the CatTrack software so that you can configure them. And once they're configured, they will roll as programmed. They interface to a number of third-party router controllers, as well as 432 or 422 and 232 third-party serial control as well. The CatTrack's configurator software is built around the idea of having a Windows application connect to our normal PERC Linux app, and that guy it can do a number of different formattings for not only 720p but all the way up to 1080p on the Cheetah size. On the Fusion will obviously go to 2160p for a full 4K resolution at UHD resolutions. The field rates are settable, and they also accommodate display technologies of VGA, DVI, RGBS, YPBR, all the different graphics computer formats that we've been used to over these many years can also be routed through our products as well. The PESA legacy goes all the way back to 1988, actually before then, but these were when we started up doing the Summer Olympic Games and the Winter Games as well. But maybe some of you have known us in other events like the World Cup and the Indy 500. The security piece is what guides us. It is our North Star. It is the anchor to our past and the guide to our future. All of our strategies support security, and this is particularly important to the government and military sectors, where they demand very, very secure connections all the way up to 4K resolutions. So security is now a new suite called Secura. The PESA Secura suite has a number of products in them that all protect the content. So the idea is that not only do we protect the control systems, but we also control the content, the actual audio and the actual video. The initiatives that I've begun over this past year and the year before, actually before that, was some endpoint development for AV over IP. And in that endpoint development comes FIPS crypto or FIPS encryption. And this is the ability to meet government certifications for not only control, but also media essence, such as video and audio, and in our case, USB. The method to do this with is the Secura Media Manager, where we've taken on components to connect to our current systems. And this is what makes up the secure control system. I'll also show you a peek at the next generation of what we're moving into, which is a lot more modern architecture designed for data centers and so forth. The certifications that we're currently focused on are the FIPS 140-2 crypto and the Department of Defense Information Network approved product list. Their lab is called JITC, or the Joint Interoperability Test Center. It's a mouthful. All these acronyms come from the government, and they're very strict certifications, and they're not ones that we take lightly, but they do take some time to get through. The suite, as it looks like right now, is our classic HTR. This is designed for our SDI routers that I showed you earlier in Fusion and in with Cheetah. These offer mid-level security, where we take the actual SDI signal and scramble that. We actually have some keys to encode them for up to 8 levels of security. We can mix and match in that setup. In the IP side, though, it's a little bit more restricted, because IP has a lot more different, a very, very different suite of certifications as they relate to IP transport. So what we're doing there is we're taking HDMI baseband, converting it to IP, encrypting it on IP and moving it around on IP using Arista switching networks. The secure KVM is just adding a USB port to that same exact box. So if you didn't need USB, you would just order the above secure IP, and if you do, you just order the bottom one with the KVM using USB as well as the video and audio with it. SDN, or software network, or software design networking, defined networking. The secure SDN is our network level control for our Arista fabric, and the secure media managers, which is how we're going to dictate how we connect endpoints together. The IP endpoint here comes in two flavors, one for AV over IP, and the other one, including USB, would have KVM. So not only would you have the video and the audio with it, you'd have the keyboard and mouse to connect as well. The endpoint takes in 4K HDMI 2.0 as an input or an output, depending on which side of the coin you are. If you're transmitting things, you'd be on the send side, so it would have an input. And on the output side, it would send an HDMI output after it receives the IP encrypted input. The FIPS 140-2 cryptography features AES 256 encryption. This is true across both audio and video. With USB, it's slightly different using OpenSSL, but it is nonetheless a FIPS 140-2 crypto standard. We have two I/O ports on this particular endpoint. It has a copper endpoint that goes all the way up to 1 gigabit per second, and the 10 gigabit per second is an SFP port that can be sent optically over optic networks using the same Arista fabric. It's lossless, very low latent, less than 18 milliseconds. It's mainly used for real-time video, which is how our routers have been used these past many years in the C2 and government installations and real-time video usage. The USB is for CAC, as well as token readers, along with HID pieces for keyboard and mouse. It does not, for example, connect storage technology, so you can't put a USB thumb drive into the slot and expect anything to happen. It won't recognize it, nor will it recognize a USB webcam, for example. What's on the horizon, what we see at least, is more of HDMI to IP transitions. We do know that 4K is being actively used in these environments, and with it, we think the flexibility of an IP switch network is where it's all going. So let me back up a little bit and explain some of the credentials that we're underway with. The Department of Defense Information Network and the approved product list. It's commonly referred to as DODN APL. This is around our video distribution system, or the VDS. 7 years ago, when PESA began our certification with DODN, we actually helped co-author this Section 9. It is for the video distribution because this was fairly new to the Joint Interoperability Test Command, or JITC. So this was the first baseband VDS certified product in there. We went to recertify that and learned a few things, and are now underway with our VDS-IP product as well. The FIPS product is just the crypto, and that's what's in our endpoint. The above, the DODN APL, is more of our system of how we do this. The FIPS piece is just identifying really the node and the encryption in and out of it. With it go with a lot of key exchanges, a lot of trusted certs and signatures, and how they're handled and so forth within the box. But that's the part of 140-2 that we're underway with in terms of certification. Common criteria, also known as NIAP, which is the US version of common criteria, comes in really two flavors. It comes in either EAL, or it comes into protection profile, or PP. We haven't done anything with this because most of our customers and clientele are in the DoD primarily. So when we finish up DoD, we'll be moving on to common criteria, so that those in the intelligence community or communities that require common criteria certification will be happy with what we do there. We'll approach it in nearly the same exact fashion that we'll do for DODN APL, just a little bit different rule set though. So the basics of how Secura works is AV over IP. This is how we take the HDMI video and transport it. And really, it's quite simple. We take the HDMI out of either the thin client or a PC or a workstation, what have you, and that baseband signal feeds our box. Our box then takes that HDMI signal, it compresses it and encrypts it, and it moves it into network fabric. We do a very, very light compression because we have used a JPEG type compression, a wavelet compression, where you favor latency over the payload. So here we don't get as great a payloads for it, but we get extremely good latency. MPEG variants do the opposite. They give you good payload compression, but they don't do necessarily very well at latency, sometimes as many as several seconds of delay. But at any rate, we take the HDMI, move it into our box on the blue side, we move it into IP fabric, and then we come out of the IP fabric, move it into the red box where we do just the opposite. We decrypt it and move it to a monitor face so that we can keep the content secured from start to finish. The construct of how we did this is based on the standards, the Society of Motion Picture and Television Engineering standards called SMPTE. And this one was based loosely off of SMPTE 2110. In there, they have a multicast flow for video, which is separate from the multicast video or audio flow. So there's two multicast flows, one for video, one for audio, and another unicast flow for USB, which is bidirectional. This is derived from the baseband HDMI 2.0 input. We take it, we encapsulate it, we encrypt it, and we move it across the network. The reason why we selected this method was because we can actually separate the video from the audio. So if the operator at one end wants to change just the video, he can select the video without interrupting the audio. If, for example, he's happy with the video, he wants to change to a different audio source, he can simply select the audio source that he's authorized to hear and move that into his monitoring position as well. On the USB, he can move that around seamlessly from his workstation points, and he can move the USB out around just as if he had an A, B, C, D, or E switcher, the little mechanical switchers of yesteryear. These are now done all in software and can be moved around on the fly with not having to clutter up the desktop. So the concept is fairly simple. We have a number of transmitters, which are shown here in blue, and they hit the IP Arista network. And then we have a number of receivers featured here in red, and we can move or connect a blue to a couple of reds, all of the reds, or just one of the reds. The idea behind multicast is I can do one to many. So that way, if another source is needed up on the knowledge wall or at another workstation area, that video can be easily seen by that workstation by simply selecting it, provided, of course, he's authorized. Here's sort of the workflow that we've been working from. These are very typical workflows. They could originate from VDI servers. I thought that would be the easiest to document here in the showing here. They could also be dedicated PCs. What I did show you though were red and black thin clients, TC. The black thin clients are going to be the unclassified, for example, and the red thin clients are going to be the classified thin clients. That network that the VDI servers are connected to, both the red and the black, are not the same network that I'm connected to. So our system is just the video and just the audio, and it does not connect directly to any of the military networks or government networks or anybody else's network for that matter. The way to think about it is that this network more or less takes the place of an old-fashioned matrix switch that you could use in silicon fabric. Now that we use IP, we would use off-the-shelf or commercial off-the-shelf switches, and in this case, we use Arista switching. The reds then are connected to, and the blacks are connected to transmitters shown in kind of gold. The secure transmitters can come from either audio video sources to the left, or they can be from PC sources shown into the right. They're connected then into the switches. The switches are connected sometimes by a spine switch. Sometimes they can be connected if they're a small enough grouping where you could do it on one switch, but for sake of illustration, I showed it this way. And then at the far end, we can separate out the blacks and the reds on the monitors, and we use our green Secura receivers to do just the opposite of what we did in the transmit side. For those agencies that insist on having these classification levels separated, we can do that as well, so that the green network, for example, is only connected to green sources and green signals. The red network, the same for all reds, and yellows for all yellows. In this fashion, they're called an air gap, so that none of the reds, the greens, and the yellows are interconnected. They're all kept separate. The whole reason for this is to make sure that anybody who's a part of the yellow or the red or the green is authorized for only what they can see. This is easy to keep track of and easy to keep mistakes from happening if there is a big collection of signals. The whole way that this is configured is using our Secure Media Manager. And this is in almost exactly the same fashion that we're being used with right now. So these systems are deployed through a lot of command and control centers that use our systems and do the same thing. They either keep them separate or they can keep them combined, depending on the need and the application and the mission, of course. In just a slightly different iteration from this, the Secura transport or the control system at the top are done with the PERC 3000 controllers that we talked about earlier. The Arista switches are combined using a leaf and spine architecture. In this case, you're seeing basically 3 leaves connected to a spine. The upper right hand is more of the control network. And then you have basically a division of, for example, different sources and different senders and receivers, so that on the left-hand side, you've got sending, and on the right-hand side, you've got receiving. You can display these for projectors, for monitor walls, or for individual baseband or feeds to the 4 points. The touch panel in the upper left also is connected to the control system, whereby those signals that are authorized for the user to select from, he selects which signal he wants, and he can put them in the monitor that he wants, depending on his particular workflow. The traditional PESA Secura pieces, and this is more of our HTR kind of connecting, is using a traditional matrix core, which can use up to 4K videos. In this case, we have a limitation in matrix size, which is one of the huge advantages when we go to IP. We don't have a fixed matrix size like we did in the old silicon matrices. For example, one of our matrix sizes that I showed you earlier was 864 by 864, but after you hit the 865th signal, you run out. There's no other matrix I can offer past that. But in IP, I can offer thousands of signals. I don't necessarily have to be constricted to a traditional matrix size. But this is kind of a traditional layout. There's really no backup. It's a very simple system, and we don't have much flexibility in it when it comes to the security aspect. On the IP switch side, we reduce the clutter on the desktop tremendously. We actually are able to do all the resolutions in one Essence fabric, so that I can also carry 1080p, I could carry 720p, I could carry 4K, or any other in-between formats that PCs typically use for their monitors. I can keep all of those resolutions and frame rates going from one connection to another, and the endpoints will adjust depending on the monitor it's connected to, or the port from the HDMI port from the PC that it's connected to, or the thin client as well. We also have encryption from all the way from the beginning to the end, kind of a source to glass concept. And I have a genuine certification using FIPS 140 and the JITC, the DODN piece for the APL. To review the release 1 feature set that I have out right now, I have an HDMI 2.0 input output. I get really low latency, less than a frame at 60 frames per second. So it's very, very hard to detect the source from the destination. So if you look at them side by side, which is one of our tests we have for our customers or would-be customers, they can see that there's very, very low latency between the two. We can control and map these flows in a fabric deterministically. and we feature under 1 gig payloads that we're moving around in the switch fabric. We could actually increase these to up to about 10 gig, depending on the user need, but most find this extremely compelling to be able to route 1 gig per second switching payloads. The box itself has a fixed key security, which is an AES-256 key. Some have their own key generation, and we can offer one ourselves. Either way, that's how it's going to work in the first generation, and later we'll have more of a dynamic key arrangement in some of our next generations. We can handle dual video, or being able to associate a side-by-side monitor, which is typically used in many of these workflows, so that you have an extended desktop, for example. We can keep track of that second monitor in the desktop so that they both are connected together when you switch them. The whole idea behind the Arista system endpoint scalability is really more the idea of a small, medium, and large. And that way it's a little easier for customers to understand how we're actually architecting the network piece. So it works in a linear fashion, so that I don't have to necessarily buy the whole big network at first and then populate it as I go, which is kind of the traditional way that we did these with fixed silicon matrices. So in this fashion, I can have, for example, 3 switches. If I have 3 switches, I can connect 144 endpoints. And in this fashion, I can more or less create a stacked array between the two. This is showing more of a leaf and spine type of architecture, although it's really not. There's a missing line between the bottom 2 switches. But if you could imagine the 2 bottom switches connected, that's exactly what that would do, so that you could trade the ports of 100 gig between these 3 switches, and in the end you'll have 144 endpoints to connect. If I start to get larger, I can take those 3 switches and move them into leaf positions and add a spine to this. And here I can go all the way up, if I add more leaf switches, all the way up to 1100 and 100 or 1152 endpoints. This fits very nicely with most of our architectures. We do have a few that are looking to be over that, and if we do, we add another mid piece in here where we can connect lots and lots of mid spines to connect other leafs, and then connect those together. And that set up, I can go well over, it's actually 36,000 instead of 3,072, but I can go up to 36,000 endpoints. These small systems are kind of shown this way as a little better represented. You can kind of see the red 100 gig ports connected using a spanning tree on the bottom switch, for example, if that's our vantage point. I see the 2 switches, and if each switch has 1 gig as an input, I can easily carry a non-blocking architecture across. I have 48 from the top, 48 from the middle. Between the two, I've got 96. And I don't count myself, so that I've got an unblocked architecture for the 2 incoming, depending on any one point of view from each switch. If I get to the 4th one, that's where I'm going to need the spine. And in this scenario, I could go beyond 144 to the 145, and that gets me to 1152 if I have 24 48 port switches to 1 spine. Now, typically I would have more than 1 spine in there in a redundant network, so that if my main spine ever had some troubles, or I had to do some maintenance on it, or it flat just didn't work, I would have a backup, kind of like a red and a blue network, where the red network is my primary and the blue network is my backup. That idea would be that it would be a second midpoint switch there. So just imagine that each switch would be connected using the 2 25 gig ports, 2 for one switch and 2 for another, for example. You don't have to, but it just, you can see the flexibility quickly. And this count in this middle system here carries most of what we traditionally architect out. And this carries up to 1152. When I get in larger systems, I can get up to 36,000 endpoints. And here I connect those 2 midpoint spines together. And then I add another kind of a super spine connecting the 100 gig ports from the mid spines to the upper spine. And now I can connect the entire network with one another, depending on the flow. Now, in order to keep that all straight, in other words, keeping the traffic managed between the uplink ports of all the leaf switches and all the spine switches, that requires a software-defined networking component. And here we have the Secura SDN component. we did this exclusively on Arista switch fabric because this seemed very logical for us to do. It was easy for us to put this together, and it really makes this simple for customers so that they just select how many endpoints they need. We kind of architect the network for them, and we can bring both the network switching, the endpoints, the control all together as a complete turnkey solution and offer non-blocking guaranteed delivery. Now, we do this with the current media manager right now, but we're working on the next gen, and we'll kind of show you what we have in place now and what we're working on in the future. Right now we have the media manager, and at the heart of it is the PERC 3000. That's the PESA Ethernet router controller. This is the third generation of the control. It features a Linux-based server, and it has blocks of code that go around it. The first one is how we connect up all of the panels together in kind of an XY basic broadcast control. And we can select sources and we can connect the destinations to them. We need to do that using an NMOS block. That network media open system is how the broadcast community began by actually using that component for registration and discovery of the endpoint. So if an endpoint comes into the switch, you'll need to know whether it's a transmit or it's a receiver or what its payload might be or what its IP address needs to be, so forth. So that's all done in that kind of elementary NMOS block. Once we have identified it, Catrax IP is the mapping tool so that I know now what I have and the address that it's at and the multicast address of it. I can now map it, and I can map it for a virtual matrix or the virtual manager. And this, it gives the ability for my my touch panels to be able to say, okay, I want to connect camera 1 to monitor 15. So he would simply select those two as the source and destination, connect them together, and away we go. Now the FIPS 140-2 module is able to fit in here in the fixed key arrangement. So this is where our AES-256 encapsulated video and encapsulated audio is encrypted and then done on a single level for management of a classified network, for example. The two pieces, which are the kind of the founding building blocks of from our original system, Virtuals has a virtual matrix for the IP. This is how they're actually switched and connected from IP address to IP address. The NMOS piece makes it register and discoverable, and the current control system of both Cheetah and Fusion routers is the same pieces and parts that we used in the PERC 3000. For Catrax, we added Catrax IP to our collection of both Catrax and Catrax J, J being the military version or the certified version of our Catrax configurator. And we do offer Catrax remote. Not too many are going to use the remote product in a secure application, but we have some of our non-secure customers using that one for remote applications where they want to control or can reconfigure the system remotely. The idea, though, behind our system is the ability to not only control the older matrix, but to control the newer IP matrices as well. So this lends itself to what we call a hybrid control. And here we can use one control system to not only cover lots and lots of different IP structures, but also the traditional secure HTR units and SDI. So here, SDI can be switched into IP, and IP can be switched into SDI. And this was kind of the mantra that we started with because we already had some of these products, and it was fairly easy and straightforward to take and modularize them such that we can control both networks, whether it can be IP or it can be SDI. So as you grow your IP network, you can reduce the SDI and then eventually have an all IP network under a lot more security, or you can simply discard the SDI and start and do all IP from the very beginning. The building blocks for the next generation, though, are quite robust. We want to get up to about 100,000 endpoints. So that'll require a fairly different architecture in terms of how we're going to build that. We did it with the idea that most of these controllers will end up in a data center. So we looked at data center architectures, and here we found not only containers and Microsoft microservices, but the Kubernetes dictate of how we manage the data and how we can distribute the data as well as SD and IP control, how we can use Arista Fabric and switching networks, and the 140-2 encryption throughout the whole control surface. This also goes true for any of the touchpads, so that when you have a touchpad, the control that goes to and from that touchpad is all encrypted. This is more or less the building blocks of the next gen piece. We did these, as I explained earlier, in containers and microservices. The idea is that you would have a particular service. It would roll out to either legacy services or future services or support services, and they would all be dictated through controlled secure web browsing, so that I can use the security of what we do in secure certs and signatures and so forth, and have a token application in here hidden in one of the services, and then I can control which apps I want to actually build for the construct that I going forward. In this fashion, we can greatly increase the endpoint counts and have a lot more control over the pieces and parts of security. So that pretty well wraps up what we're doing here at PESA, and if you've got questions, I'd be happy to take them. There's a lot in there, I understand, but it gives you a great vantage point of seeing where we're going and some of the pieces and parts that you'll be seeing from PESA very soon.
Kevin Baskel, back on with you. I'm trying to get my camera back on with you right now. I have a couple of questions, and I made some notes because you had a lot of acronyms in there, which is great because you do a lot of government work, and at times it sounded like you were speaking a different language.
Yeah.
But that's okay as well, because a lot of times my wife says I'm speaking a different language, just when I'm talking about regular work. But the last things you were saying seem to resonate with me about building our control rooms, our back rooms, our back offices like more like a data center, less like a control room, and that's where you guys were looking towards, which makes a lot of sense to me. Can you expand on that
Sure.
a little bit more?
Yeah, so the third generation of our controller, we actually moved from hardware to software, which was a big leap for its day. And we foresaw that any changes you need to make, it definitely influenced more of the hardware side of things. So with software, we had a lot more flexibility. In all of these constructs, though, it's a very monolithic type server, so that I can back up that one in a redundant array. But after I go past that, or I turn off either one of those two boxes, in this case, if you had a redundant, you'd turn them both off, you have no control. Where would that go to? So the data center approach seemed to us fairly logical. And one of the pieces that we saw in this is the limitations that we had with these monolithic controllers. And what I mean by that is that when you start to expand an SDI router past its original kind of studio, if you will, to another building or another facility, or maybe even another city, this is where the controllers don't do well. They need connections to another controller, or the handoff, and there's a big scheme in that. Or we have to star balance everything. In other words, if we have one building as a main campus building, then we can fiber out to all the other buildings, but we still have a home run to make in the central core route. What we're thinking is that in a data center approach, we could have the data center parked nearly anywhere. We could have it on campus, as long as they've got connection to any of those. We could build back-end services such that when one service went down, it would dictate where you go to the next one. So in this fashion, we could go from New York to Los Angeles to Hong Kong. We could do a number of different connection pieces using data center technologies. That's not always the case in military, because those are all kind of cordoned off, but it's the same architecture used, whether it's a public cloud, a private cloud, or even a government cloud. And in this sense, we see the controllers moving around as they're needed. So this way, we can move the control of our flows depending on where it makes sense for the application or the mission in some of our military customers. This is also true of expanding outside of government pieces. So if we had, for example, corporate, where corporate has, say, 3 main cities, and they need to coordinate some pieces for the seniors to seek confidential video. This could be accomplished using the same sort of architecture that the corporations are using for either centrally based servers or servers that are distributed. So that's where these Docker and containers and all the pieces and parts of how we manage the database and how we back that up and how we move it around are all into play when we move it into a more modern architecture in that fashion.
Well, right here is a perfect example of what we're doing here with this virtual NAB Plan B, because I want to take a whole lot more time with you, and I want to actually have you come here so we can dive deeper, or me go there into your booth and dive deeper. So I'm going to take a little bit more time with you, if you don't mind, and dive a little bit more deeper into your questions. But this is what our customers should be doing with every manufacturer that's out there. So dive deeper a little bit. But I'm not going to take too much more of your time. But you mentioned government, and you mentioned the encryption, and you also mentioned corporate and the encryption. And I think that's really important, especially when we bounce off of the data center idea and where we're going as a entity, as a whole broadcast system. So they're both important. And you mentioned FIPS. How does that fit into it with the encryption? Are you guys the only guys that do that?
So yeah, so we took the high road on that idea. So instead of just offering for example, an AES-256 encryption or AES-128, or you can choose a number of different encryption schemes. We decided to go down the FIPS route because these are requirements that we are already in environments where they're required. And so the highest level of security that we could think of was, in fact, FIPS. Now, FIPS is the Federal Information Processing System, at least if I'm not mistaken. These acronyms are rather new to me as well, but I do know this one, that the standard for that was developed by the National Institute of Standards and Technologies, or NIST. And NIST has within its confines what they're doing is in FIPS. So they're saying, okay, well, here's a crypto that you could use. Tell us how you're going to manage the keys and how you're going to turn it off and how you're going to protect the content. And these are the threats that we see, and we want you to go through a series of tests. And over the course of about 1.5 years, we go through these tremendous scrutiny of our endpoint to make sure that it has met everything that NIST can come up with for it. And then at the end of that, we get a certification for it. We know in our heart of hearts that it's a good, solid encryption scheme. And so for other uses, it's obviously overkill, but if you stick with a very high standard from the very beginning, why not? These are government encrypted standards. We can use them in nearly any application, and the same thing holds true, for example, with medical. Patient information is highly regarded, and it's very sensitive. It's very confidential information, and we want to protect that, even when it comes into video for that particular patient or whoever is conducting this, and as an institution, a hospital, a medical facility, etc., a learning institution for medical. Those are all pieces and parts that can use our encryption to their advantage to make sure that they can comply and make sure that that video is in fact protected and squared away.
Well, because we also know that in medical, it doesn't have to be educational for video, because everything is videoed, from somebody's heart rhythm to an ultrasound. It's all on video.
Right, exactly.
So
and with it go,
keep that protected.
Right, that's a great great point. The thing about it is that there's a lot of metadata that goes with that patient. For example, you'll have some data about the patient, and you'll want to kind of keep this all together so that flows that are not only real-time video, it could be real-time audio, it could be real-time data that goes with it. In other words, the patient's heartbeat, the vitals, all of those pieces and parts of data that go along with the video could be associated with that in this architecture, so that they're all kind of kept together. Those are tremendous advantages that we see, at least initially. There'll be other applications where security can be used in the same fashion, where sensitive information isn't for everyone. In other words, they want to keep it protected. And so what means do they have in the video side of things? We know of no one who's actually applied for FIPS certification for both the video and the audio essence packets. They have for example, on the control side of things, but not necessarily for video and audio directly. So we know that we've done some good hard work in terms of making sure that we're going to be there, as we were from nearly 7 years ago when we brought the first thing called a router to the military and government folks, and they said, well, what the heck is this and how are we supposed to test it? And we said, well, sit down, we'll teach you how we did this. And they adapted some of their rule set for us, and it applied to all the vendors that came after us and for their video distribution systems as well. So we're doing this kind of all over again. This time we're going to do this with an IP set as opposed to a silicon SDI set.
So you don't know of any other boxes out there that use FIPS encryption?
Well, yeah, let me clarify that they might use parts of the FIPS, which might be some control elements. For example, UDP might be protected, but what about the multicast flow for video? That we know hasn't been done. The multicast flow for audio, that we know hasn't been done. There might be for other pieces and parts of the system, but we're not aware of anything, or at least they haven't been filed as discreetly as open and saying, okay, these are used for this media, and here's how we protected them using these FIPS standards. That is not there.
Now, just for a point of clarification with me, when you mentioned AES 256 keys for encryption, is that the number of keys that we're talking about, 256?
No, that's
there like
size
3
of
keys?
Yeah, it's a good question. So the AES 256 is the 256 hex bytes that go with it. So it's a large number, for want of better. So if we had a password that had 256 hex bytes long, using 0 through F. So if you know your hex, you'll go all the way to 16. For each counter, you go over 256 bytes and you'll have the number. So it's a fairly long number, is the point. That has to be randomly generated. The randomness of that is determined, or a thing called entropy. And entropy is the measurement of how random you have. In other words, if I generate a number, can I say that that number probably won't occur again? If it's truly random, it won't reoccur. It could, but that's how they're measured, and there's very strict tests about how the entropy is measured. But the idea of a very long password is where the 256 comes into play. So I only have one password. It's extremely long and complex, but if you guess it, then you're in. That would be a hard task to do. It's more about the ability to change that out for a mission. So for example, if I want to protect my content and I use this particular key, I might use it only for a couple of hours, and then I could change it out if I wanted to. And that's the randomness of getting another password, so to speak, to put in.
All right, I just did want
Excellent question.
and again, that was one of the things that flowed into. It was just supposed to be one question, but if you see the pattern here, it just keeps flowing like a conversation does. And
Sure.
It really was just one extra question. And here's another one that flows into it, because we started talking about medical, but we're in the video industry, and then we popped over into the data center industry.
Yeah.
And now we're talking about medical. So PESA's in the medical industry now, talking about doing videos there. You know, we're talking about heart rate videos and all this other stuff. What other industries is PESA going to be in aside from the military and now medical?
Well, you know, we've certainly been approached by some industries where quality control is extremely important for video, and that video is very sensitive video for the way the company and that our client would be addressing, and how he makes or builds a certain product, or fabricates a certain product, or has a certain process that's only he knows about, right? He uses this video. It's a very precise video, and he wants to make sure that that video is protected and secured, but yet available in real time. So we've used in processing manufacturing, where the process is extremely sensitive. So that's just one example, and they may have different data that goes along with it. In fact, some cases the data is actually more than the video, if you can believe that. So not only are they using some of the video for quality control, they're also using the video to make sure that the process is repeated in exactly the same fashion for every run they do. So that's just one example, but anywhere that you have video that is important and key to the operation or the patient or the mission or a rocket launch or what have you, anytime that video is your video and you don't want that video to creep out, that's where you're going to need encryption. And you're going to make sure that that the video that you are capturing or that you're viewing in real time, however, you want to make sure that that is absolutely as protected as you can make it.
Now, when that's protected, does it have to be protected under an SDN, under a software-defined network to protect it?
Yeah, so that more addresses the scalability to it. So depending on how many endpoints you're dealing with, will this network start to flex its muscles, so to speak. So for example, if I have, oh, I don't know, let's pick 100 endpoints. Well, I know from my examples that I gave earlier that I can fit 100 endpoints easily on 3 switches. And if I connect the endpoints directly to one another, I don't need SDN at all. In other words, I can assure you that my 1 gig of payload from any one of the ports that are connected into the network won't be blocked. Now, why is that important? Well, as you know, if we block video, we get a stutter in the video, and it's not appealing to watch or view or record or what have you. We expect unblocked architectures to help us be able to make a video flow that's uninterrupted. And this is kind of from our past. This goes all the way back to the analog days, to the SDI days, to the early HD days. We expected and demanded that the video was never interrupted. And when we move this to an IP structure, that game is definitely in jeopardy, because as you know, in a business network, I might interrupt my colleague to the left of me who is doing a print job. And that print job may interrupt me for a little bit. I don't mind. It's a computer network. It doesn't really get too fussy if the print spool is loading up and buffering, and so that's all fine. But in video, I can't do that. I don't get to use those kinds of tricks. What I have to adhere to, though, is making sure that once I begin a flow, I don't interrupt it. So that as I connect box to box across the ports on a network, I want to make sure that I have a full 1 gig payload that cannot be interrupted. Now, when I get to larger endpoint counts, when we get up to say 500 endpoints, then I'm going to need a lot more than I can do with just the trick of connecting the big uplink ports to one another and expect to have a non-blocked architecture. That trick doesn't work anymore. So now I have to be able to manage each of those switches uplink and downlink ports to one another, so that a flow from one switch goes all the way through the network and gets received on another switch, and that the ports in between are adequately managed so that we don't oversubscribe them. In this case, we would use a whole bunch of 25 gig uplink ports. I don't want to ever exceed any one of those 25 gig uplink ports, because if I do, I upset the whole thing and the network will crash. It's an oversubscription and they don't handle that well. And so I have to have some management piece in here overseeing the idea of having, for example, a 48 port switch that has 2 25 gig uplink ports. I want to make sure that those 2 ports are being managed and balanced, so that I have, for example, I'll pick a number, 12 gig on each payload or port, so that I have I have 12 gig on one port and 12 gig on another. I don't have, for example, 5 gig on one and 20 gig on the other. I want an even balance. So as I come to the mid plane switch, the spine switch, I have an even distribution of payload. This also ensures that none one of these streams that are connected use a highway that's more or less congested. So it's like getting on the 405 at the wrong day or wrong time of the day. and pretty soon you're just stalled, right? So you want a nice clean path that you're not interrupted. You're driving exactly your 1 gig per second speed, and you're making sure that nothing's in your way, and you're connected all the way to your far endpoint without any obstruction. So you need a vehicle that does that, and that SDN vehicle is what we use to manage the Arista switches in the network.
So the Arista switches are the fabric. The Secura boxes, now that they fit into this under the SDN, are they the endpoints that we're talking about, and do they fit on your desktop?
Yeah, so they can fit right behind your monitor. We tried to go for one of the complaints that we heard in the C2 environment was they were sick and tired of all the clutter on the desktop, the extra box, the extra wires, the this, the that, and they wanted that all cleaned up and tidy. So we managed to make sure that the box could fit neatly behind a monitor, integral to that, and so that really you've got a keyboard and mouse, and that's it, and a touch panel for the control.
What plugs into the Secura box? Just a fiber plug-in?
Yeah, so there's 2 ports on the Secura box. One is used when you want more than 1 gig, which would be up to 10 gig, for example. You can use the SFP port. If on the other hand you need PoE, the copper port, it can fire the box up for power. It can also be done in under 1 gig payloads along with control and the audio and the video. So depending on how you adjust the compression on the box dictates which port you want to use. Now, some environments are strictly fiber only. So in that sense, we might have a restriction of 1 gig on the SFP port, but we're using fiber out in and out of the box.
Right.
We don't ever use fiber on it.
That's great. So it's great for the military applications. It's great for the medical applications. I mean, everything is in the fiber world right now, and that's a wow. That's an amazing use for it, and it plugs in right behind the monitor. Scott, this has been enlightening. I don't want to take up too much more of your time. I think this is great. I'm going to stop my questioning right now because I know you have other places to go, but I do want to continue this. I have a lot more questions. As you can see, I've made a lot of notes during your presentation. I've got a lot more questions. I think we can dive deeper into some things, and hopefully we have a lot more customers that we can work together on.